Welcome. In this video, I'm going to talk about the last section of 10.1, where they talk about classes of compounds. So the activity of the functional group is often limited or influenced by which carbon in the stem it's attached to. Is it an on in the end? Is it an inner carbon? Is it off on a branch? Because that will limit how easily other things can get in and react with that functional group. So the classification of primary, secondary, and tertiary carbons is used to describe the carbon that the functional group is attached to. So a primary carbon is when the carbon attached to the functional group also has at least two hydrogens. So that means it would have to be the end of a carbon chain because it's attached to the functional group, it's attached to two hydrogen. That only leaves one more bond to attach it to one carbon. A secondary carbon is a carbon attached to a functional group plus one hydrogen and then two other carbon groups. So this is going to be some kind of an inner carbon. So it does have one hydrogen on it. It does have the functional group on it, but then it also is in the middle of the carbon chain. The carbon chain is branching off two directions on it. A tertiary carbon is a carbon attached to the functional group plus three alkyl groups. So the carbon is in the middle, so it's situated between three carbon groups, and there's some kind of branching within that hydrocarbon. So the functional group is attached, but no hydrogen are attached, and so it is known as a tertiary. It's got three other carbon groups attached to it. So one way I remember it is with the primary carbon, there's only one carbon attached to the carbon with the functional group. Secondary carbon has two carbons attached, and the tertiary has three carbon groups attached. So if we take a look here, I've got some examples for you to try. It says, identify the class of carbon in the following molecules. And you might want to draw the structure. Otherwise, you might be able to visualize this in your head. And the first one, written the first way, it's not necessarily so easy to visualize, but looking at the second one, it should be pretty easy to visualize that you've got a carbon with three CH3 groups attached to it, and then the Cl group. So this is a tertiary carbon. Whereas the second one, I have a CH3 group attached to a CH2 group and an OH. So this is a primary carbon. And then my last one, if I scroll down a little here, I have a CH3 group attached to a CH group with an OH and another CH3 group. So this is my secondary carbon. And again, one, two, or three carbons attached to the carbon containing the functional group. And the reason this makes the difference is hopefully you could see that this chlorine is going to be awkward to get to because you've got branches sticking out in several places. Just like this OH might be somewhat cumbersome to get to because you have the CH3 branches sticking off here. And I didn't draw the hydrogens all around, but if you think about the hydrogens sticking out in all three directions, you can see where this could be cumbersome to something coming in trying to get that OH off, whereas the primary carbon is going to be the easiest or perhaps the most reactive of these three types. Amines also use a classification to show how many alkyl or carbon groups are attached versus hydrogen, but now we're talking about the nitrogen instead of a carbon atom. And just like with the carbon classification, if there's one carbon or alkyl group attached to the nitrogen, it's primary. If there's two, it's secondary, and if there's three, it's a tertiary nitrogen atom. And again, these alkyl groups limit how easily other things can come in and react with that functional group. And then the other thing to talk about in this final section, classes of compounds, is this idea of cyclic or ring structures, or the arenes. The arenes are a class of compounds that are all derived from benzene, C6H6, and they form a special branch of organic compounds called aromatics because they have strong scents, and these can be pleasant or not so pleasant depending upon your opinion. Benzene is a 6-carbon structure in a ring or a hexagon, and for a long time they assumed it was with alternating double and single bonds and one hydrogen per carbon. As it turns out, it's planar. The C6 and the H6 is all in one plane, and there's many derivatives like TNT where hydrogen is substituted with other elements or groups to give you that variation. And so then the substituted benzene molecule is a functional group called the phenyl, and that's the functional group for arenes. It's an important compound in industry because of its unique behavior, and it's commonly used to make drugs, dyes, and plastics. Another just little quick aside, it's also carcinogenic, so its use and disposal, handling and disposal, both need to be carefully regulated or paid attention to. So think about it. Because benzene has 3 double bonds, or is highly unsaturated, you would expect it to be fairly reactive. You got 3 double bonds that you could easily go in and break one of those bonds. So especially an addition reaction should be a possibility. And also, scientists have realized benzene has no isomers. There is only one way to draw benzene. So these two characteristics help scientists, and especially a German fellow named Cyclic, realize that benzene is a cyclic or ring structure, not a straight chain. But benzene is also super stable with low internal temperatures, so then they were still stuck with what about these alternating double and single bonds that it seems to have. So what Cyclic came up with is he said if this has to be a ring structure and it's only 6 carbon with only 6 hydrogen, the way to do that would be if every other one of these was a double bond, then each carbon would need just one more hydrogen to make it stable. So for a long time, this has been the common conception, and for a lot of people, it still is the common conception of what benzene is. And you'll see it abbreviated to look like this, or you'll see it abbreviated with the circle here to show that scientists would expect this single and double bond to resonate or move between the 1,3,5 and the 2,4,6 carbons. But because it's not very reactive, they did more research on this and this idea of the alternating double and single bond. And what scientists have come to realize that each carbon in benzene actually forms 3 single bonds. It forms a single bond with a carbon on each side, plus a single bond with the hydrogen atom. And that leaves 1 unbonded electron per carbon atom. But instead of forming the alternating double bond, these 6 electrons actually are delocalized or free to move, just like they are in metallic bonds, and they're shared among all 6 carbons. So at any time, a pair of those electrons might be closer to one of the carbons than the others. So these 6 electrons are shared both above and below the plane where the 3 single bonds form between the neighboring carbons and the hydrogen. Okay, so it's similar to a pi bond forming. I just want to show you a structure. So up above were the possible structures for benzene, C6H6, before they realized that it was actually cyclic or a ring structure. And then the second structure shows Cyclic's alternating bond model. And then the current model below shows how in one plane you'd have the carbons and the hydrogens single bonding, each carbon with 3 bonds. And then you would have the pi orbital extending above and below this planar structure. And when those pi bonds, or those pi orbitals move closer that they can overlap, you form this donut above and below. And like I said, it's very much like a pi bond. And electron density maps have shown that carbon bonds are all the same length, and they seem to have equal density around each carbon atom. So that gives great strength or support to this idea that it's actually 60 localized electrons being shared equally among the 6 carbon atoms versus a resonating or alternating double and single bond.